Today's lesson is solving linear trigonometric equations. And let's really talk about that title before we even get started here, because a lot of what we'll see in this lesson, we've already seen in other lessons. This is just tying a lot of stuff together. So this lesson's really good at bringing together a whole bunch of ideas that have been coming together for a long time here. Okay, so what does each part of this title mean? First it says solving. So what that really means is we're going to find the theta values, or the x values, or whatever the unknown is in the question. What does linear mean? Linear, we're going to be, well, it's easier to talk about what linear is not. Linear is not going to have no exponents, no roots, nothing like that. So we will see in these trigonometric equations, we'll see sine, and we'll see cos, and we'll see tan, maybe even secant, cosecant, and cotan. We'll see those things, but we won't see sine squared and cos squared. These are just solving linear ones that don't have exponents on them. So we open up with an easy one that opens up the idea that there's going to be a big problem with finding the answers here. It says, consider the following trigonometric equation, sine x equals 1. If we go to solve this equation, we'd be looking for all the values of x such that sine x works out to be 1. How many solutions exist? Well, right off the hop, I can see sine x is equal to 1 there, and it's equal to 1 there, and it's equal to 1 there, and it's equal to 1 there, and it would keep going like that. My graph doesn't have all of the answers on there. It has 4 of the answers. There'd be more and more and more answers. And so that's a problem with solving trigonometric equations. When we solved regular linear equations in grade 9, we'd get one answer. When we solved quadratic equations, we'd find that we could get no answers, or we could get one answer, or we could get 2 answers. The problem with trig equations is we'll get an infinite number of answers. And how do we say something like that there's an infinite number of answers? Well, by looking at the graph, we see sine x equals to 1. Okay, the first one is here at pi over 2. And then when does the next one occur? 2 pi away. So it goes pi over 2 plus 2 pi before we get to another answer. When does the next answer occur? Plus another 2 pi. So it's every 2 pi after that. So how we express that is we mentioned the first one. We say, okay, well, x could equal pi over 2, and we get to sort of choose what the first one is. I could have chose some different ones. I chose pi over 2 here. And then what other answers do we get? Every 2 pi. So we go, oh, plus every 2 pi. So we could put n at 1, and we'd say, okay, we need 1 2 pi's. Or we could go 2 2 pi's or 3 2 pi's, however many 2 pi's you want to get to other answers there. So the possibility of an infinite number of solutions is a result of the periodic nature of the sine function. But lots of times what we do is we just look for answers between 0 and 2 pi, just in that first cycle. So both answers are possible, or both questions are possible. Sometimes we might be looking for an answer in one specific domain, like for between 0 and 2 pi, or sometimes we'll be looking across the entire domain. So just to get used to these questions, we'll start off with ones that are just between 0 and 2 pi. Or in that first cycle, let me put that, or 0 degrees less than or equal to x, less than or equal to 360 if we're going to work in degrees. So let me just do a warm-up example, and I'll do this one in radians, just to get a warm-up going here, to show you that you've seen some of these linear trigonometric equations before, that it's not really something new that we're doing here. And as the new things come in, I'll specifically address them. So it says solve for cos x equals negative 1 over root 2. So the first thing we do is we go, okay, well, cosine is negative, so I want to draw where these angles could be. And if cosine is going to be negative, there's 2 possibilities. In that first cycle, in that 0 to 2 pi cycle, we could be cosine negative in the sine quadrant there, and so we'd get an angle in the sine quadrant. But there's another quadrant where cosine is negative, and that's here in the tan quadrant. And if you're confused already, take a look at cosine. This is what cosine is going to look like. There's the first lap of cosine. And when does it come out to negative 1 over root 2? Well, somewhere in there. And then it does it again somewhere in there. Some values in those 2 spots there. So there's 2 different spots where it comes out to be negative, in the sine quadrant and in the tan quadrant. Well, and the nice thing here is they've given us sides that are right in the special triangles. They don't have to do that, and as the lesson goes on, I'll show you how to deal with it if they don't give you special triangles. But it's nice when they give you special triangles because you can label your special triangle on there and put your special angle here, which is pi over 4 in the triangle, and that'll be the same sides in this one, 1 root 2 with a pi over 4. And with those diagrams, I'm now ready to answer. My first x value is this angle here. So x could be this angle here, which would be 3 pi over 4. If you're still having trouble with these kind of radian angles, just remember pi, in this question, we'll think of pi as 4 pi over 4. And this angle doesn't go all the way to 4 pi over 4. It goes 1 pi over 4 less than that, so I get 3 pi over 4. Whereas this one does 4 pi over 4 plus another 5 pi over 4. So the other x possibility is 5 pi over 4. Now, I did that one in radians. I'm going to switch back to degrees in just a minute so that if the radians is confusing you, I want to show a few in degrees so that you can see that don't let the radians confuse you. If that example seems totally familiar, yeah, this lesson isn't, it's going to add a couple little new things as we go along here, but the basic idea is to solve for x when there's a trigonometric equation going on here. Our steps are draw the angles and use the special triangles to find the angles that you need there. So the examples that are provided in your note say to do all of these in degrees. Well, I'm going to do the first few in degrees, and then I'll switch over to radians because I don't want you to get so hung on degrees that you can't do radian questions. At the same time, I don't want to start you off on questions that you have trouble with because of the radians. So we'll start off with degrees. The first example in the notes says sine theta equals root 3 over 2. And this question's a lot like the example that I did above. Is you just say, okay, well, where is sine positive? I'm going to start doing some color coding here. Where is sine positive? There's two different spots that sine is positive. Of course, it's positive when you look in the all positive quadrant. Right there. So there's the all positive quadrant. And then it's also positive when you go to the S positive quadrant, which is right in there. And they told us that opposite over hypotenuse was root 3 over 2. So there's root 3 and there's 2. And in this diagram too, there's root 3 and there's 2. So opposite over hypotenuse, root 3 over 2. And so in degrees then, this related acute angle is 60 degrees right in the special triangle there. So what are the two answers here? Well, theta in the first picture could be 60 degrees, or theta could be 120 degrees with the related acute angle being 60 degrees. So I get two different answers in the first cycle. Incidentally, if you're wondering how you answer this question, if it wasn't just in the first cycle, I'll just put that in green here. After that, you go, well, okay, plus 360n. So plus every 360 degrees, you'd get another answer. So how many n's? Well, that's up to you. You can add 1 360 or 2 360s, 3 360s, however many 360s you want in there. So I just put that in green there so that you know that doing this for an infinite number of answers is really not a big step. You just got to add on to that, that period there. Okay, the next example that I want to do is one that involves secant. Secant theta is 2. So you want to solve for secant theta equals 2. Now, you can do this question in secant if you want. It's not really a big problem to do it with secant. And maybe I'll try and mention that in the middle of all this, how you would handle it with just using secant. But I think most people are more familiar with cosine. So what they do is they go, okay, secant is 1 over cos, and just do a little rearranging here and solve for cosine, because they're a little more familiar with cosine. And what I get is cosine theta equals 1/2. Nicely in isolated form there. Just mentioning that because we're going to get to some questions later where it's not so isolated. And so then I draw my two quadrants where cosine is, we're positive here. So cosine could be positive in the C positive quadrant. Cosine could also be positive in the all positive quadrant. And here we have adjacent over hypotenuse is 1 over 2. So I get a 1 there and a 2 there, and a 1 there and a 2 there. Between 1 and 2 on our special triangle is 60 degrees. So, whoa, another question with 60 degrees as the related acute angle. So my two answers here, I'll do this one over here first. Theta could be 60 degrees. That's that first quadrant answer. Or here, theta could be 300 degrees. So it's not all the way around. It's not 360 degrees all the way around. It's only 300 degrees. So not too bad. Those should be very familiar type questions from the previous lessons. Number 3. So each question now just adds on another little component to this. This one, tan theta equals negative 0.1944. So it's tan, so it's not a problem like the last question where it's not a familiar trig ratio. This is just opposite over adjacent. But knowing what the related acute angle here is a bit of a problem. When the ratio that we're given is a ratio we're familiar with, like root 3 over 2 or 1 over 2, things that are in the special triangles, the special triangles give us the information we need to find the related acute angle. This question doesn't give the related acute, or doesn't give something that's in a special triangle. I mean, there is a triangle out there that has opposite over adjacent equals 0.1944. It's just not special, that's all. It's not one of the special triangles. To find that special triangle, what I say is, okay, I'm going to go after this related acute angle here. And to go after the related acute angle, I'm just going to say, okay, oops, not that. I want the related acute angle will be the tan inverse. So I'm just going to do the tan inverse of this of 0.1944. And as I write that, it could be you're screaming, oh, what about the negative? Well, I'll deal with the negative in a second. When you're finding related acute angles, you have to ignore the negative part of it, because the related acute angle, it doesn't take on that negative part of it because it's an acute angle. It doesn't go into other quadrants. It will never be negative. So, and I'll draw a picture of it in just a second. Trust me for now, that what we want is the tan inverse of the positive number here. And so when I type that in my calculator here, tan inverse of 0.1944 in degrees, because I'm still doing questions in degrees here. I'm going to switch over to radians in just a minute, but this is a degree question. It says 11 degrees. So the related acute angle is 11 degrees. Let me draw what I'm talking about here. Same as the previous question, there's two different quadrants where this answer could be. The spots where tan is negative, right there. So I am going to use the negative now. I'm going to say, okay, so where is tan negative? Well, tan is negative first in the sine positive quadrant. So there's where tan is negative. And the other spot is where cosine is positive in this quadrant here. And each time, the related acute angle is 11 degrees. So there's what the 11 degrees is. So that tan inverse move I did was really making the triangle special, if you want. Instead of the other questions where I had a special triangle already, by doing tan inverse, I was looking to make that triangle special by going, okay, I'll do tan inverse of this thing, and now I know what this triangle looks like. It's got an 11 degree in it. That'll give the 0.1944 that I'm after. And then I ignored the positive part because I knew I was going to take care of that with the cast rule anyways. All I wanted was the acute angle of 11 degrees here. And then I can answer the question fairly easily. This angle here would be 169. I go 180 minus that 11 degrees. And this one here, 360 minus that 11 degrees, 349, I think. And so therefore, theta equals 169 degrees, or theta equals 349 degrees. Now, an interesting part of all these questions is, right now I'm just reaching for my calculator and I'm typing in tan of 169 and I get negative 0.19438, rounded to 0.91944, and I get the negative. I can check these answers so nicely. So if you miss a positive or negative, as long as you're checking the answers, you'll catch that positive negative thing with your calculator. And then I'm going to go tan 349 and negative 1.438. I've got the two answers there. Okay, so that was 3 questions in degrees. I'm going to jump ahead here and go into some let me use this spot over here. Now I'm going to go to do 4 questions in radians here. So I'm going to go like here. We're going to say theta is less than or equal to, or 0 is less than or equal to theta is less than or equal to 2 pi for the rest of the questions. So if you sort of understood what I was doing in those questions and the degrees made sense to you, then now we'll just try and expand that knowledge and try and do some radian questions instead. Okay, and this question ties everything together all in one example here. So it says we want cosecant theta to be equal to negative 1.7013. Lots of stuff going on here. The first thing is that it's cosecant. So to get it into more familiar terms, I'm going to rearrange this into 1 over sine theta. And then when I cross multiply and divide, I get sine theta equals 1 over negative 1.7013. And I'm just going to leave it just like that. I could divide it and get the decimal if you wanted to, but you don't have to. It's nicely in a fraction I can use there. Now, this 1.7013 is not in a special triangle. It's not like a root 3 or a 2 or a 1. So it's not a special triangle. Well, I'm going to make it special. It's going to be special for this question because I'm going to go after the related acute angle here. And instead of using a special triangle, I'm going to use my calculator to go sine inverse of 1 over 1.7013. And I hope the last example showed you that I don't want the negative part. I'm just going to go after the positive version of this because it's an acute angle. The answer won't come out to be negative for the acute angle. I just want that angle I can use to find the other part. If you don't like that answer, I'll say it another way. The other way is I'm going to take care of the negative when I draw it in the quadrants with the cast rule. I don't want the negative to interfere right here. Now, I do have to make sure I take my calculator and switch it over to radian mode here, because then I got to go, not theta. Whoops, major error there. Not theta. Related acute angle will be equal to the sine inverse of that. So my related acute angle, when I type that into my calculator, in radians, I get 0.61. 2 decimal places, pretty good for these type of questions, okay? So again, double check on your calculator. If you're not getting the same answer as me, make sure that you're not in degree mode anymore because this question asks for radians. And then you can type in sine inverse, open a bracket and go 1 divided by 1.7013. And when you do that, you should get what I get, 0.6. Oh, I just copied that down wrong off my calculator there. Glad I checked that. When I type that in, I get 0.63, not 0.61 there. But if you type that in and you round wrong, it's easy to get off by a decimal place or 2 there. So I was a little more careful on that version of it. Now, 1.713. Okay, so I've got related acute angle of 0.63. Now that's really intimidating. When you see 0.63, you're like, something must be wrong, but it's not. Radians are a much smaller measurement, if you want, and that to go all the way around a circle, you're only going 6.28, so 0.63 is a significant angle. These numbers are going to be smaller when you talk about radians, so don't get intimidated by that. That's right for radians. So now to draw my picture, where I'm going to take care of the negative part of this. I want the quadrants where sine is negative, so I need this quadrant here, the tan quadrant. That's where sine is going to be negative. And then I need the cosine positive quadrant. That's where sine is going to be negative. And so this related acute angle is 0.63 both times. And okay, big moment here in your understanding of radians. What's this angle here? And I want to rewind to something I did earlier that just was probably easy when I did it with degrees, is like to get this answer here of 169, I just took the 180 degrees and subtracted 11. I just went right past that. You're sort of used to degrees that was a pretty obvious move. Well, this time it's not quite so obvious because we're in radians, and the question is how much is the angle just to that negative x-axis there, and it's pi. So to get this answer here, I want pi plus this 0.63. So that's a very strange answer when you put it in. You go pi plus 0.63, but your calculator will give you the decimal answer, and you should get something like 3.77. Okay, very weird. If that blew your brain a little bit, I totally get it, because radians are sort of new in all this, and it's not easy to think in radians. But remember, pi is the same as 180 degrees. When we're thinking in radians, we're thinking that that flat angle is, instead of being 180 degrees, we're thinking of it as pi. And so when you do that, you do get the decimal answer, 3.14. So then this one, all the way around, well, it's not quite all the way around. 2 pi would be all the way around, and we've got to take 0.63 out of that. So the theta is equal to 2 pi minus 0.63. And when I type that into my calculator, I get 5.65. Again, if you're off one decimal place due to rounding and so on, that happens in these questions based on how much rounding you're doing there. Okay, that question had it all. That is a beaut. It had cosecant, it had non-special triangles, it had radians, it had everything going on there. So that example might take a couple of looks before you really get used to all of those steps. And just to add on to it, now, those questions might actually have seemed pretty familiar. This question is the first one that really is really new. Here's what this lesson is supposed to all be about: solving a linear trigonometric equation. See, all of these ones I did before, it was already isolated. In number 1, it was already sine theta equals. Number 2, it was already secant theta equals. Number 3 was already tan theta equals. And number 4 was already cosecant theta equals. I'm not saying that made it easy, but we didn't have to isolate the trig ratio to begin with. Well, the rest of this lesson really is just about isolating that trig ratio to begin with. See, we don't have this equal sine theta equal to something. It's root 2 sine theta minus 1 equals 0. But you've solved the equations before. Before you even start here, we just have to isolate the sine theta. So the 1 gets moved over and becomes positive 1. And then I divide by the root 2, and I get sine theta equals 1 over root 2. So that's what's really new in this lesson, is isolating sine theta. I don't think you're going to have too much trouble with that part of it. Now to go through all these steps again. Sine theta equals 1 over root 2. And the important part about that is we're talking about positive 1 over root 2. So we want to be in the all positive quadrant. And in the S sine positive quadrant. And this time, I don't have to use sine inverse because it's a special triangle. It's 1 over root 2, which we immediately know the related acute angle. That's pi over 4. And so my two angles here are possibly pi over 4 or, okay, so this would have been 4 pi over 4 if it had got all the way to that axis, which is, pi is 4 pi over 4, but it didn't make it all the way. It was pi over 4 short. So it was 3 pi over 4. So we'll just do another one with cosine. 3 cos x equals cos x plus 1. Again, the difficulty with this is cosine is not isolated to start off with. So that's what we do. We bring all the cosines to one side. And they'll collect up nicely. And then divide by the 2 to get cos x equals 1/2. Now we're in business. I've solved for cos x, and now I can draw where these angles will be. The important part of this is cosine is positive, so I want to be in the cosine positive quadrant and the all positive quadrant. 1 root 2, 1, 2, ooh, careful now. So many root 2's in this that it's easy to get hung up there. There's 1 and 2 and 1 and 2. So then the related acute angle, you got to have your special triangles memorized. That's a pi over 3 in there, and that's a pi over 3 in there. So my two answers, x could be pi over 3 in this picture, this one here. Okay, all the way around would be 2 pi. But I've got to subtract pi over 3 over that. So I'm going to think of 2 pi as 6 pi over 3, subtract a pi over 3, and I get 5 pi over 3. All right. Last example, number 7, a butte. This one can confuse you, and I'm going to show it in just such a way that hopefully it won't be all that confusing. When you see sine 3x equals 0.5, all I need to do is tell you that when you've got a number inside of sine like that, all we're going to do is deal with this at the end. Okay? And I'm going to go back to degrees here. Because there's a little thinking that has to come at the end that the first time you see this will be a little easier to see in degrees. So sine 3x equals 0.5. Now, again, the 3x, I told you, we'll deal with it at the end. Okay, so sine 3x equals 1/2. So we're talking about a sine situation, and it's got to be 1 over 2. So far, so good. This is not a big deal so far. I got to be in the all positive quadrant or the sine positive quadrant. I need opposite of hypotenuse, 1 over 2. So far, so good. If opposite of hypotenuse is 1 over 2, we're talking about a related acute angle of 30 degrees. And so that means, and this is the first of the tough parts of this question. The first tough part of this question is that it won't be x equals 30. It'll be 3x equals 30. And it won't be x equals, well, what's 180 minus 30 is 150. It won't be x equals 150. It'll be 3x equals 150. And I said we deal with it at the end. Well, then we just got to divide by 3. So I get x equals 10 degrees. I divide by 3, I get x equals 50 degrees. Okay? So when there's a coefficient inside the sign, don't worry about that. Just ignore it. Just leave it in there and carry it around with you. It's 3x was all through the question. And at the end, you just got to divide by 3. Now, if that was all there was to this question, it would be pretty simple. But there's another part to this. So I went back to getting answers between 0 and 360. And what I want to do is draw a little sketch of what I've got here. This graph here is sine of 3x. So what that means, if I went to draw it, it wouldn't have period 360. It's been compressed by factor 3. The period, I'm just going to draw a little thing here so that I don't get confused between the questions here. The period of this graph would be 360 divided by 3. The period's 120 degrees. Okay, so what I've got is, at 120 degrees, this graph will have to have gone up, down, back, here. Okay? And what we found is, when is it equal to 1/2? Here and here. 2 different times in that first 120 degrees. But the only problem is this question said find the answer between 0 and 360. This graph keeps going between 0 and 360. See, at 240, it'll have gone again. At 360, it'll have gone again. So it's got to go, there's my little nudge there. It's got to do that, and then it's got to do that, and do that. So there's more answers here between 0 and 360. So I've only got the 2 answers. We need this answer, and this answer, and this one, and this one, all these other ones. Well, that's the bad news. The bad news is you have to know to look for these things because we've only got 2 of the answers here so far when there's a coefficient on the x because it changes sign to having more answers between 0 and 360. Well, finding the other answers is easy, though. How do we get from this answer to the next answer? That's plus 1 period. That's just the answer on the next period. So the period here was 120 degrees, so we'll have other answers. Oops. X equals, there'll be one at 10 plus 120 degrees. So there'll be another answer at 130 degrees. There'll be another answer at 130 plus another 120 degrees, which is the period. So I get another answer at 250 degrees. And if I add another 120, I'll get the 370, which is outside the 360, so I don't need that. There'll be another x at 50 plus 120 degrees, 170 degrees. And then there'll be another answer at 170 degrees plus another 120 degrees, another answer at 290 degrees. Let me highlight all those answers. 10, 130, 250, 50, 170, and 290. And hopefully you can see in the graph there why these other answers pop up is because we've changed the period here. That is difficult to tie all those things together in one question. So these need practice, folks. You've got to go through these and beat your head on them and work through all the little details here, because there's a ton of little details that's built up in here in trig, and I promise you that all these little details are going to matter as you move farther ahead with trig and into calculus. So please give those some thought.